We're going to look at combining like radicals now. Now the problems we've done up to this point have all been some form of multiplication or division. Well, when we have addition and subtraction, we have to follow the same rules that we did with regular variables. For example, if I have like 2x plus 3xy minus 4x, I can only combine the 2x minus 4x because they have the exact same variables on them. The 3xy I can't combine with anything because it doesn't match any of the variables. And now when I combine like radicals, I would take my 2 minus my 4 and then keep my label. So do you remember the tigers from the other chapters that we've done? If I had 2 tigers plus 3 tigers, I would end up with 2 plus 3 tigers, which would be 5 tigers. Now, even though I have my label appearing twice, since I'm adding them, it doesn't appear twice. I just add the coefficients out in front and then keep my label. Well, we have the same idea when we're combining like radicals. So if we come down here to this example, I have 3 fourth roots of 7 plus 6 fourth roots of 7 and then minus 2 square roots of 7. First thing you have to do is identify which ones are like radicals. Well, in order to be like radicals, you have to have the same index and the same base. So these first two are like radicals because they're both the fourth roots and then they're both a base of 7. This last one does not combine with anything because it's missing the fourth root. It has the same base, but it's a square root, so it's not the same thing. It's kind of like having an xy instead of just an x. So when I look at this, I've got 3 of these things plus 6 of those things. Well, 3 plus 6 gives me 9, and I still have fourth roots of 7s. This fourth root of 7 is kind of like the tiger. I've got 3 tigers plus 6 tigers. Well, I have 9 tigers. Then this square root of 7, I don't do anything with. I just write it out as minus 2 square roots of 7. So when I were to combine these like terms, I would have 9 fourth roots of 7 minus 2 square roots of 7. So our combining like terms when we have this addition and subtraction is different than when we do multiplication and division. Okay, here's a practice one for us. So I've got 3 square roots of 5 plus 2 square roots of 5 minus 3 fifth roots of 5. You have to go through and figure out which ones are identical, and it would be the square roots of 5. The reason this one doesn't match is because it's a fifth root, and these other two were square roots. So I would take my 3 plus my 2, gives me a 5, and I have a square root of 5 yet, and then I'm just going to bring this last piece down because it doesn't match with anything. So minus 3 fifth roots of 5. Okay, another one that we have. 2 cubed roots of 5 plus 6 square roots of 5 minus 8 cubed roots of 5. On this one, my first one and my last one are matching because they're both cubed roots of 5. So it's almost like they're 2x and minus 8x. And then this is some other variable. Maybe it's a 6y because it doesn't match identically. So when I take this 2 minus 8, I get negative 6. I have negative 6 cubed roots of 5 and plus 6 square roots of 5. Okay, another one. Cubed root of 16 minus 3 cubed roots of 2. Now this one might not be as obvious because they don't look like they match. But what you have to realize is that this cubed root of 16, we can break it down. If you go to your cheat sheet and you go to the cubed column, you want to figure out what can you divide 16 by that's on that list. Well, you can divide it by 8. So I can break this down into the cubed root of 8 and the cubed root of 2. Well, my cubed root of 8 is 2, so I actually have 2 cubed roots of 2 minus 3 cubed roots of 2. Now I actually have like radicals because I have a cubed root of 2 and a cubed root of 2. Well, when I take 2 minus 3, I get negative 1, so I have negative 1 cubed roots of 2. So that one we had to break down before we could combine them. Hey, this one looks a little different than the other ones did. We have 7 times 6 to the 2/5 plus 2 times 6 to the 2/5. What you have to realize is that this is a radical. Remember, rational exponents we can write as radicals, so this would actually be the 5th root of 6 squared, and this would also be the 5th root of 6 squared. So we do have like radicals even though they're in exponent form. What you have to understand is that you cannot take this 7 times 6, because the 6 really isn't just a 6. It's a 5th root of 6. We can't multiply those two together. Same thing with the 2 and the 6. I cannot multiply those together because it's really not just a 6. It's a 5th root of 6. So if it's going to help you out to rewrite it using radical notation, then go ahead and do that. When I put these two together, I have 7 of these things plus 2 of these things, so I'm going to have 9 and then 6 to the 2/5 power. I cannot multiply that 9 and 6 together because it's not just a 6, it's really a 5th root of 6. Here is another set of practice problems, and we're going to have to simplify these a little bit of a different way. So I've got the cubed root of 125y to the 6th. Now there's a couple different ways you can look at this. I would probably start by breaking them apart into the cubed root of 125 times the cubed root of y to the 6th. If breaking them apart is going to help you isolate them, then go ahead and do that. First thing I want to do is I want to see, can I break down this cubed root of 125? Well, if I go to my cheat sheet and I look in that cubed column, 125 appears on the list. Track it over, and the cubed root of 125 is actually just a plain 5. Now this cubed root of y to the 6th, what you have to think about is how many groups of cubes can I get out of y to the 6th. And what I mean by that is this 125, I could have rewritten it like that, because 5 cubed gives me 125. So when I take the cubed root of 5 cubed, those actually cancel each other out, which is why I just end up with this 5 here. Now this cubed root of y to the 6th, there's 6 y's underneath here, and I need to see how many groups of 3 I can break that into. So I can do one group of 3, and I can do a second group of 3. So when I take the cubed root of y to the 3rd and y to the 3rd, I can break it apart just like we did to start with. And this first cubed root of y to the 3rd, well, that'll completely cancel it out, and that'll give me a y. The second cubed root of y to the 3rd will also cancel out, and that'll give me another y. So what I'm really left with is this 5 from before, and then these 2 y's. All my radical signs have disappeared for this one, so I really have 5y squared, is what that one would simplify down to. Another way that you could have done this one would have been to change this y to the 6th to rational notation. So you would have had y to the 6 over 3, and 6 over 3 reduces nicely into y squared, which is what we ended up with. The thing about doing rational notation is this is not always going to reduce down just perfectly nicely. So let's jump over to the second one. I have 9u squared v to the 10th, that quantity raised to the 1/2 power. Now this one, you can rewrite using radical notation. You can multiply it out first. I'm going to go ahead and multiply this out. Now remember, our rules of exponents is that everything inside here gets this 1/2 power. So I have 9 to the 1/2. I'm going to have u, and when we do power of power, we multiply exponents. Well, 2 times 1/2 is 1, and 10 times 1/2 is 5. So I really have 9 to the 1/2, u to the 1st, v to the 5th. Well, based off of my exponents, this is the only one that's still a fraction, so it's the only one that's a radical anymore. And 9 to the 1/2 is really the square root of 9. And then this u to the 1 is just out here by itself, and this v to the 5th is out here. Well, the square root of 9 reduces all the way down to 3. So we actually have 3uv to the fifth for this one. Okay, our third example down here, I have 6xy to the 1/2 over 2x to the 1/3 z to the negative 1, or z to the negative 5. I'm first going to move this z to the negative 5 up to the top because I don't want to have negative exponents. And then I'm going to pick my regular numbers to work with first. So this 6 and this 2. Now remember, they're regular numbers, so they follow the regular rules. So I really just have 6 divided by 2, which is a 3. So I'm going to end up with a 3, and that takes care of my 6 and my 2. Next, I'm going to focus on my x's. I have x to the 1/3 on bottom and just an x on top. Well, my rules for division say that I subtract my exponents, so I need to take this 1 minus 1/3, and that's going to give me 2/3. So I'm going to end up with x to the 2/3. That takes care of my x's. Now this y to the 1/2, it doesn't get to combine with anything because there's no other y's. So we have y to the 1/2. And the z to the fifth doesn't get to combine with anything, so we have z to the fifth. Now, I've got a couple of radicals in here. I've got a 2/3 and I've got a 1/2. But what you have to realize is that since these fractions, this 2/3 is not an improper fraction, I won't be able to break it down like we did in this problem up here. Same thing with the y to the 1/2. My fraction's not improper, so I have to leave it. A couple other things you would want to check for is, do you have to rationalize? Well, we ended up not having anything left in the denominator, so we don't have to rationalize. And this 3 only has an exponent of 1, so I don't need to see if I can break that down. So this one would be done. Okay, this next one, I have 8 cubed roots of y to the 4th minus the cubed root of 27 y to the 4th plus the cubed root of y to the 4th. Well, I've got two like terms right here. I have the cubed roots of y to the 4th and the cubed root of y to the 4th. This one looks like it has potential to match because I have a cubed root, and inside here I do have a y to the 4th, but I also have a 27 in here. So I can't combine it right now, but I might be able to break that down, or I might be able to work with it and see what we can do. So the first thing you need to do is go to your cheat sheet list, and you need to check if you can break the cubed root of 27 down. And you should notice that 27 is actually on the list. So this cubed root of 27 is actually just a 3. So I have 8 cubed roots of y to the 4th minus 3 cubed roots of y to the 4th plus the cubed root of y to the 4th. Now, only the 27 broke down when we did this. So this y to the 4th right here is still underneath the radical sign. Now I have all like terms there, so I can go ahead and combine them. I've got 8 of these things minus 3 of these things plus, now there's really a 1 here, so 8 minus 3 plus 1 gives me 6. So I have 6 cubed roots of y to the 4th. So I've got those 3 terms combined down into 1. But there's one more thing I can do with this. I have an index of 3, and underneath here I have 4. So if I were to write this using rational notation, I would have 6 and then y to the 4/3. I have an improper fraction here, which tells me I can pull some of those y's out. So when my exponent underneath is bigger than my index, I can pull some things out. So what I need is groups of 3, because that's my index. I'm going to break this y down into y to the 3rd, and then you have to ask yourself, how many y's would you have left over? Well, if I put 3 of them here, I would have 1 more. So I'm going to have the cubed root of y to the 3rd and the cubed root of y. I still have that 6 out in front. Well, this cubed root of y to the 3rd cancels out, so I'm just left with a y out in front. So I'm going to have 6y and then the cubed root of y.